Hello everyone, good day. We are on the 4th week and this is our lecture number 16. In the previous lecture, we have seen some of the spectacular brittle deformation that we could see in and around Ghatshila. And today, we will not really be in the brittle zone, but we will take you to the Shinghum shear zone in a particular place called Rakha mine. So, we will work beside an abundant copper mine, and then we will do some strain analysis using deformed conglomerates. After that, we will come back again to the Ferrighat, where we will do the same practice, that is strain analysis using deformed convolutes, and then we will show you some other things. So, we are here in the middle of Shinghum shear zone, and the location is near the Rakha mine. So, Rakha mine is on that side, Rakha copper mine, and we are at the west side of Rakha copper mine. In this place particularly, this particular horizon is very interesting and important in order to find the kinematics of the shear zone, particularly at this place, very precisely. And the reason is I am standing on a horizon which is of deformed conglomerate, which is very unique in this region. And if you look carefully or observe that overall this is the foliation plane of the shear zone. So, this surface is the foliation surface of the shear zone, and you can see they successively go this way. So, this one, then this one, and then here and here. Let me give you the orientation of this horizon. It is 122 degrees. There is also one very important thing to look at here. The Shinghum shear zone is actually a thrust shear or thrust fault, large scale thrust fault. It was on the surface, and down there it was a reverse shear. And if we look at this plane, so essentially the dip is in this direction, right? And if we figure out the x direction, so this indicates the down dip lineation, and that is also something important. So, the long axis of these ellipses actually gives you the stretching lineation as well, and this tells you that these are down dip lineations, which are also very important to understand the kinematics of a thrust induced shear zones. So, we are on another horizon of this Shinghum shear zone, and this place is about 200 meters away towards the south of this conglomerate bed that we looked at, and the rock here we see is quartzite again, but the look of this quartzite, as you can see, is completely different. So, we see that let me take the measurement here. The trend of this entire horizon is 116 degrees, and you see these are the overall foliation planes of the shear zones, and This is the major foliation, and then some other conjugate sets probably have developed, but this is the major foliation of this shear zone, and we see this down dip lineation throughout. So, apparently this may appear in a first look that this could be slickened sides, but these are not, because we see them in each and every surfaces. So, thin section study of these rocks revealed extreme ductile deformation of the quartz grains. The temperature that recorded maximum was 600 to 700 degrees centigrades. So, therefore, grain boundary migrations and other features are very evident in these rocks when you look at them under optical microscope, particularly the transmission light microscope. So, as we said that we are in the shear zone, and this conglomerate bed is well within the shear zone. But one obvious question that might have come already to your mind is that where are the shear zone features even in the conglomerate bed, because this shear zone is known for high shear strain. And in this exposure and few other exposures, I will now show you some very important and interesting shear kinematic indicators that will tell you that we are actually in the shear zone. Ductile shear zones are characterized by number of fabric development inside the shear zone, and at the same time some very interesting asymmetric structures, which are kind of characteristic features for ductile shear zones. For example, we know that if C and S fabric, these two interact with each other, they form some rhombic shapes, and with further rotation these rhombic shaped blocks take the shape of some sigmoidal features. So, what we see here, for example, we can see some kind of things here. Okay. So, these are the traces of, as you can see, this is the shear zone foliation. So, we can consider them as C fabric, and then we see the S is going like that here, and therefore, we form a shape of sigma. And you see also the clasts inside, they are deformed synthetically along with this. So, that tells you the shear sense is sinistral. If we focus a little further from this place, we can also see a fold like feature. We see this fold is asymmetric, and again it tells that it moved in sinistral motion. The fold axis is down dip and almost giving rise a reclined fold. If you are not convinced with this, I request you to focus in this place. You can see a beautiful S shaped fold. The fold axis of this is something like that. Shear zone foliation is this. So, again we form a reclined fold here, and the shear sense is sinistral here. In this section, we also see a very similar feature. For example, if you follow this particular pebble, you see it is going like this, coming this way and this way, and this form is also a folded form, and we clearly see that this is an asymmetric fold. Fold axis is plunging to this direction. This is the foliation plane. So, therefore, fold axis is making a high angle with respect to the foliation plane. The pitch of the fold axis is at high angle with the foliation plane, giving rise a reclined fold. The shear sense is here also sinistral. So, in a shear zone, if you would like to understand the kinematics, what is most important is to identify the kinematic planes, and I particularly select this exposure. What we see here, this is the foliation plane, shear zone foliation plane, and that means this is the xy plane of the shear strain ellipsoid, right, or kinematic strain ellipsoid. And if we see here, we see the conglomerates, they are stretched. You can see this is their long axis. For example, this one is a single pebble that got stretched like this. You can see one here got like this. So if this entire plane is xy plane, and we see this is the long axis of the deformed pebbles in this conglomerate, so clearly tells that on this xy plane, this is the x direction. Once you fix the x and this plane is xy plane, and we know that x and y are mutually perpendicular to each other. So if this is x, then this must be the y. Once we fix that, we look for a perpendicular section, rather two perpendicular sections of this area or this plane to find out yz and xz surfaces. And xz surface, at least in this place, is important because that would also may help us to figure out the kinematic indicators in terms of shear strain and so on, and we will see if we can figure out or not. So this plane in particular, if we focus on, we see that this is the xy plane, that is the x direction. So in this side, this should be also x direction. This plane is perpendicular to this plane. So if this is x, then this must be the, you can spell it by yourself because y is going in this direction. So this is x, this is y, so this must be the z direction. So this plane should be x z, where x is in this side and z is in this side. We can go to the next plane. So we have defined xy plane, we have defined xz plane. Now if we come to this side, on this surface in particularly, this is almost a sub-horizontal surface. We can see this is the xy plane again. So this was your x, this was the y. So in this side, this is y, that direction, and because this is x, so this must be the z. So we have yz plane. How beautifully this exposure displays xy, xz and yz planes. Now in all these sections, we have the deformed conglomerates exposed, and the beauty is, if we measure the long and short axis of these deformed conglomerates at these three sections of number of pebbles, then we can plot them in Flynn diagram and figure out what was the overall strain distribution in this area. So we are looking at xy plane of the kinematic strain ellipsoid, and what you see here is the stretched conglomerate pebbles, and you can see they are elliptical in cross section on this xy plane. The x direction is down dip and y direction is the shorter axis of the elliptical cross sections of these pebbles. Now I am looking at xz section. The xy section was this one, and you can see that xz section is perpendicular to the xy plane, and on this xz section you can see the stretched pebbles of these conglomerate beds, and you can easily recognize this white, highly stretched and with very strong elliptic pebbles. The long axis of these pebbles are much higher, the length of the long axis of these pebbles are much higher compared to the shorter axis. So, the long axis is the x direction and the shorter axis are the z direction in this section. Now, we are looking at YZ section, and what we see here, the stretched ellipses are there, but they are of little different shape. The y axis here in this section are longest and the z axis are the shortest. So, we have identified the three kinematic planes of this particular area, and to be very specific, this deformed conglomerate terrain. We have also observed the stretched conglomerate pebbles. So, this was the xy plane, this was the xz plane, and this was we have identified as yz plane in different sections or in different little exposures of this area. What are we going to do now? We will measure the long axis and short axis of these stretched pebbles. Whatever we get along our trajectories, we will measure and take notes of them, and then we will measure it in each section. So, on xy section we will measure the long axis of the ellipses and short axis of the ellipses. So, we will get x and y. On this section, that is xz section, we will measure the long axis and the short axis, therefore, we will get x and z, and in this section which is yz section, we will also measure the long axis and short axis of these stretched pebbles, and there we will get y and z respectively. So, we will collate all these data, plot it in Flynn diagram and see what was the nature of the overall strain here. Now, what I will do, I will give you a very basic theory of how to plot them and how to interpret them. So, in the next couple of minutes, you will see or you will hear the basics of Flynn diagram, and then we will plot this data in the Flynn diagram and we will show you how does it work and what are the kind of strains that this particular section of Shingbum shear zone received here. The description of three-dimensional strain ellipsoid is best represented in Flynn diagram. So, in 2 dimension, the shape of the strain ellipse that we have described by only one number, that was r, which was the ratio of long axis versus short axis. But in 3 dimension, the shape of the strain ellipsoid is described by 2 numbers. One is r12, which is the ratio of long axis versus intermediate axis, and another one is r23, which is the ratio of intermediate axis versus short axis. Now, the ratio of these 2 parameters, that is ratio of r12 and r23, describes and distinguishes the different shapes of the strain ellipsoid, and this number is known as k, where k is defined as r12 minus 1 divided by r23 minus 1. So, from this equation and our understanding on x, y, z, we can figure out that minimum values of r12 and r23 possible is 1, and k can be from or could be equal or greater than 0 and equal or less than infinity. Now, given this condition that k could be 0 to infinity, so you can report the all possibilities of strain ellipsoids in the Flynn diagram. And the Flynn diagram we will see in the next slide. It is two-dimensional Cartesian plot where x axis is represented by r2 3 and y axis is represented by r1 2, and you can plot a number of k values in between. So, the diagonal of this plot, as we will see soon, that is where r1 2 equal to r2 3 is actually defining the plane strain condition, that is y axis of the finite strain ellipsoid is constant during the deformation. That means we have learnt it before that there is no stretching or no shortening along the y axis. Whatever deformation happens, that happens along the x and z axis, and therefore on the xz plane. So, this is the Flynn diagram we are talking about. As you can see that along the x axis we have plotted this, and in this case this is again long axis which is x, and here this is y, and again all these things is under log. So, this log is used to accommodate different shapes or sizes of the measurements. So, different magnitudes of the measurement. If you have a high value and if you have a small value of the measurements, then you can plot everything in the same diagram. Let us try to understand this diagram in detail. So, as we said that along this line which is running 45 degrees with respect to this x and y axis, this is where k equal to 1, and as we have said k equal to 1, you have plane strain at constant volume. As you can see here, at this magnitude of strain, the y axis remained constant. Even I increase the strain magnitude, y axis remain constant, but it extends along x and shortens along z direction. So, whatever left on both sides of this k1 value, if I go to the top side, that says that it is under the constriction domain. That means that in this domain everything would deform along x axis, it would extend, and other two directions it would shrink. Therefore, with progressive deformation you would produce something which is like a pencil or like a long object. On the other hand, if we go to the flattening side, which is the downside of this k equal to 1 direction, there the deformation would happen in axially symmetric manner or axially symmetric flattening manner, where x is greater than or equal to y, and this x y values are much greater than z. Therefore, you would produce something like a pancake or like a flattened disc. So, if I go towards this side k equal to infinity, then I produce rocks characteristically with some sort of linear features, and if I come to this side k equal to 0, the deformed rock would show a lot of flattened objects or disc shaped objects. Now, considering this idea, you can figure out if I am in the constriction domain, then the rocks would tend to produce more linear features through deformation, and at k equal to 0, the rocks would tend to produce more flattened or planar fabrics. So, we have measured now the data of these deformed conglomerates. So, we saw them exposed in xy plane, xz plane and yz plane of the kinematic strain ellipsoid. Now, we have plotted the data in this Flynn diagram, and you can see that it is coming towards the flattening side. So, some data you also see that they are on the plane strain direction, but they are mostly falling in the flattening side. if I request you to concentrate on this particular section, this is the horizontal surface, this is a subvertical surface, then if you are little expert on theory and more or less have seen the photographs, images, or have done some field work, you may immediately say, ah, this is a shear zone and it looks like a protomyelinite, because you see a lot of fabrics, then you see some clasts here and so on. But I tell you, this is not the case. What we see here, this is overall some concentration of traces of bedding planes, you can see all over, and you also see a fabric that is going like this all over. These are S1. So, this is S0 and S1, they are almost subparallel to each other. And then all these little things that you may recognize that these are clasts, but I tell you these are not. These are some thin sedimentary features. So, they are concentrated load balls and some small tiny convolutes. You see them in different places. Now, you can certainly ask me, why do you say so? The reason is, inside these you can see sedimentary features, tiny laminations and so on. So, that confirms you that these are not a myelonitic structure or protomyelonitic structure, but load balls and other thin sedimentary structures. Now, the significance of this place is this, that as I said, this is the S0 plane. So, you can measure S0 plane here by taking lineation of these traces on this surface and this surface, and you will get the orientation of S0 and also S1. And this plane is also exposed here and there in this place, this S0 or S1 place. So, we can also go and measure there. So, this is the XY plane. You can take the measurement of XY plane by measuring the lineation here of these traces on this plane, on this subvertical plane, and also measuring the lineation here on this subhorizontal plane, and plot them in the stereo net to get the orientation of the XY plane. This XY plane is also exposed here and there in this section, and we can go and measure them directly as well. What is important, all these sedimentary features here, you see they are deformed, they are stretched, and we do not see XY plane exposed here, but we have to determine that what is X, what is Y and what is Z, and luckily we have some perpendicular sections. So, what we see here, all these clasts here are stretched and these clasts here are also stretched. So, if this is the XY plane, then Z must be in this direction. So, these two planes, this one and this one, they contain Z. So, clearly Z is the shortest. So, this one is Z and this one is also Z here. So, this direction is the Z direction. Now, it is important here to determine what is X and what is Y. So, either this could be X, this is Y, or this could be Y, or this could be X. Now, if you examine the elongation of this deformed sedimentary features, we see both are elongated here in this surface and here also on this surface. Now, the elongation here is more, that is, statistically if we try to measure, we will see, or we try to look, that this long axis in average is more than here. In other ways, we can say that these features are more elliptical, or ellipticity is higher on this surface than this surface. That leads us to conclude that this must be the X direction and this must be the Y direction. So, in this surface, without visualizing the XY plane properly, we can conclude that this is Y, this is X and this is Z. Now, we can measure the long and short axis of all these ellipses exposed in this is YZ section and this is XZ sections. And we can also measure them on exposed foliation surface, that is XY plane and long axis and short axis. And eventually we can plot them in a Flynn diagram to understand the overall strain behavior of this place. So, we will see some other places where we have measured this ellipses on YZ plane, XZ plane and also on XY plane. We are looking at YZ section and these are the top cut of the convolutes along the YZ section. We are looking at XZ section. This section is not perfectly XZ, little oblique, but we did not have better section than this, so we are measuring it. We are looking at XY section and we are seeing this stretched sedimentary features on XY plane. Now we have plotted the data in this Flynn diagram and you can see that it is coming towards the flattening side. So, with this I conclude the lecture number 16 and I hope I could give you some very brief ideas of different kind of brittle deformation and the strain analysis that we do in the field from deformed markers. In the next lecture, we will perform a general overview and overall discussions of this field course and we will try to build a general structural understanding, a three-dimensional structural understanding of this region. Stay tuned, I will see you in the next lecture.